People filter in, we will begin. And indeed, we have begun. So, today, so I have one bit of information to share with you, and feel free to share it with Marco if they hopefully they'll listen to this. Let me put it this way. Something interesting happened, and I understand I have no objection. I'm I have a son who is extraordinarily familiar with AI. In fact, he is, I'll brag a little bit, he is sort of the AI guy for the surface warfare for our U.S. Navy. So, a big deal. And don't ask me, they stuck him with the job. Nevertheless, I have one of the students in another section who basically took my verbal study guide and threw that into Chat GTP and said, make an exam. Do that. If you haven't done something like that, I don't object. AI's a headache. I mean, if you're in a class and you're going to see, for many of you going into some of the nursing and health science, and if you have to do reports and research stuff, be careful with that because I mean they're very concerned about plagiarism and not citing and all that type of stuff. I could care less. I only want you to get it right. The emphasis. This is all about getting the questions right for now and going forward. And so I'm fond of saying, no one is going to ask you about the events at the neuromuscular junction site. Did you know that those were chemically gated channels that let in three sodiums and put out two potassium? Nobody in the world is going to ask you about that. Okay, but it's part of the curriculum, and it basically is your ability to understand those things. I was amazed at how basically I obviously spoke clearly enough for them to figure out at least they got the answers right. You're getting what I'm telling you. Good, thank you. So endeth the sermon. Everyone say amen, that type of thing. So we digress. Let's see, okay, nobody has any messages for me. We'll begin. This is all about the synapse and neurotransmitters. This is really how the nervous system sort of converses with itself. Don't forget to tell her what you just missed. Good. Thank you. Inevitably, I'm telling the people who are here, and as opposed to the people who will never listen to this, who are not here. But we digress. Okay, moving on. So this is really about the conversation it has. There's a lot of synapses. The basis of this chapter is really about chemical synapses. There's a couple of electrical ones. There's a myriad of different ways the nervous system interconnects with one another. We are basically interested in something. You'll see the term is called axodendritic. The axon is the transmitting end, for the most part. The dendrite is the receiving end. The message is basically the conversation is expressed in chemicals. That's the classic one we're looking at. So take that as the frame. So it's information flow, the synapse or synapse, whatever they want to call it, from one nerve to another or from one nerve, just like the neuromuscular junction, to an effector cell. There's so many synapses, the language, and this becomes a little bit confusing. And I try to stay away from it from a test perspective, are called, at least for this class, this level of class, pre and post synaptic nerves. In a pathway, there could be hundreds of these. So the presynaptic is the one sending the message, and the postsynaptic is receiving the message. That's all. Okay. And again, in the peripheral nervous system, basically, it could be the message could be going to a nerve, a muscle, a gland, and they're absolutely true. Most of the time, it's both ways. There's so many that it's receiving information from one and it's transmitting it to another, and simultaneously having conversations with multiple nerves coming in and going out. And this is what they're showing you. They're showing you just some examples of the ones here in graphic form. This is the one we're really interested in. This one's called axodendritic. You have to know the name. I'm not going to ask you the name about axodendritic or anything like that. But that is how the conversation is basically taking place. You're sending signals from here and they're contacting. It looks like it's direct contact. It is not. Sometimes the conversation can go directly to the soma or the cell body. Okay. And basically think of it as almost modifying it. It's almost like, here's the information. This is really important, or just keep this in the back of your mind. Maybe it'll be that kind of. I'm trying to give you some examples of the way I would try to understand it. And even as you're transmitting, it could be, you better get that, send it out special delivery. We want FedEx overnight versus, whatever. We could send it fourth class mail in the old days. Do you understand what I'm trying to sort of convey to you? Is we can modify the signals, whether they're incoming or outgoing, but the basic signal is coming in by way of a chemical that being released at the axonal end of this guy in blue and received by this guy in this golden color at the dendrite. And here it is, for real, in a micrograph. So whether it's, there could be synapses all over, and in general, there are a lot of them. So that's the context, again, for you to become familiar with. And you can see all of these. These are the big players. Axodendritic, that's the one we're focusing on. Yes, we can have some modification by other messages. And you can see all of these other ones. And really don't have to remember any of these names. Okay. And really, we're going to focus on the chemical synapse as opposed to the electrical synapse. I just want you to understand that they're all there. Chemical. Neurotransmitters. You're going to get sick and tired of hearing about neurotransmitters, particularly going to about the 10 of them you need to know something about. But you already got one of them down. You already have acetylcholine. So typically composed of two parts. The axon terminal contains the same thing we've talked about for neuromuscular. The areas are interchangeable in that regard. Synaptic vesicles filled with the neurotransmitter, neuromuscular junctions, acetylcholine, and a receptor. And it just happens in the nervous system. It's typically another nerve, neuromuscular junction. It's that motor end plate, usually on the dendrite of the cell body. And yes, same deal as the motor end plate, a fluid-filled cleft, a space, an extraordinarily small space, but yes, a space, and yes, it's filled with fluid. When we get to, if nothing else, I'm sure by this time you've got a concept of how, when we get to molecular small or atomic small, how freaking small that is. I mean, to be able to have all those, acetylcholinesterase and proteins like that are huge compared to isolated atoms and molecules. So the space can be extraordinarily tiny to us, and we still have a lot of stuff in it. So the electrical impulse is changed to a chemical across the synapse, then back to electrical. Again, that's the rate determining step. That's where things, if it slows down, and it does slow down compared to instantaneously, but by no means slow. So the synaptic cleft prevents the nerve impulse from directly passing. It's chemical. It depends on how rapidly it's released, how rapidly it goes across, how efficiently it binds. And yes, again, unidirectional. The big thing with the nervous system is the action potential and the direction of communication is typically in one direction. Inside the nerve cell, stuff moves back and forth. You might remember previously when we looked at the cells, unfortunately, that's the way diseases sometimes, you talk about polio or tetanus, they actually can follow this because that nerve cell is still busy sucking back stuff up, absorbing fragments, reproducing stuff. And that mechanism can be the term we would use as hijacked or taken over in such a way for that. So that's what makes that, the nerve is kind of unique in that. The transmission is one way, but it utilizes two-way stuff movement in any event. I don't get anything out of this one, so I'm saving it. So you can look at it if you wish. So, and this is the way it works. This is the sequence of events, very similar to what you already learned. The action potential, bang, just like in the neuromuscular junction. Good old, there they are again, voltage-gated calcium channels doing their thing. Calcium, extracellular calcium, enters the cell from outside to inside the axon terminal. Boom. Same way the neuromuscular junction starts. Okay. The transmitting of signals, it's hard to see with these illustrations for me. Here are the neurotransmitter, there are the calcium channels, here's the impulse coming down, and here's the receptor area. Again, it's not as intricately arranged sort of shape-wise or in the way, and you can see it from this illustration, we're not dealing with a motor end plate, we're just dealing with receptors. But they are chemical, and again, the other name is ligand receptors. So you just see the same thing here, and when it opens up, basically these exocytoses, and it spits out tons of chemicals that are there. How rapidly, you're going to see how rapidly they're spit out. Are they spit out in one location? Are they spit out in multiple locations? All of those things matter. So this is the way it works. You don't have to know this, thank goodness. Okay, the chemical that causes this is called synaptotagmin. Don't ask me why. And that's those snare proteins, the ones that are associated with botulism again. Basically, it doesn't allow them to fuse. But with the calcium activates, this is how it works, this particular protein, and basically facilitates that the snaring of the synaptic vesicles and allowing them to fuse and exocytose. The higher the frequency, the more they exocytose, the greater the effect. Frequency equals amplitude. That's why. They're showing you a little bit there. The neurotransmitter diffuses across, binds, and the receptors are very specific. You're going to see that there, and that's the complexity of the nervous system. There are receptors for more than one neurotransmitter because nerves usually produce 2 or more neurotransmitters. Most nerves, not all. That neuromuscular junction thing, just acetylcholine. So that's, again, we're looking at an additional level of complexity that's here. And the and it opens those channels. And again, just like end plate potentials, here we call them graded potentials. Change the shape, ions channels open, graded potentials, and they can be either excitatory, fire, or inhibitory, don't fire. It all depends on what chemicals they're leading in or leaving out. That's the way it works. So it could be opening sodium and potassium. That would typically be excitatory. If chloride is being able to be brought back in, that's going to make it more negative. That's inhibitory. It depends on the neurotransmitter. And I will give you a basic construct about what they use. Sometimes you can't predict. Sometimes it depends on the nature of the receptor. All receptors are not created equal in that regard. So same deal here. If you can read the fine print, good luck. Here, and here are those graded potentials. And again, localized changes, unless it gets to that magical area or those abundance, what we discussed last time, voltage gated sodium channels, ain't nothing happening. So I used to say in my old neighborhood. Neurotransmitter effects. We already got this. Reinforcing, same kind of question you're going to see. Shh, don't tell anyone. It's a secret. Told you, my son's in the Navy. Loose lips, ships. All he knows is to give orders. Terrible person. Neurotransmitter effects are terminated. There's 3 ways. It can diffuse away. It can be degraded or metabolized. Remember, breakdown, degradation. So it diffuses away some of the acetylcholine. Some of it's broken down to its component parts, acetyl radicals, or acetyl. Basically, we saw acetic acid and choline, and reuptake. It sucked back up the choline. And they all do this to some extent. They all do it differently. They don't necessarily do all 3, but it can be, any of those can be involved. Basically reinforces what you got before. As long as the neurotransmitter is binding the receptor, the graded potentials will continue. Okay? And so there's a way of regulating it. We have to keep pulling it out to effectively create an abundance. Remember, it's frequency. So there's one signal. Now we have to resignal and resignal and resignal. So basically that involves the nerve spitting out more neurotransmitter that are there. And they're just showing you too, and I can't get a lot of that bottom graphic. The delay. This is the rate determining step. I'm so fond of using that. That's the difference between flying to California and talking to somebody in California right now. Okay, and what is that? 0.3 to 5 milliseconds. That's a sufficient amount to change how rapidly nerves conduct business, to bring them down with those myelinated nerves to, oh, I don't know, 100 meters per second, whatever that converts to in miles per hour, 200 meters per second. It's how fast that is, and this just slows it down. The rate limiting, I said that before, of the neurotransmission. Transmission action potential down axon can be very quick, but the synapse slows transmission to postsynaptic neuron down significantly. Not noticeable because they are still, would you substitute the word very with at least another adjective beginning with an F and ending in ing, fast. Freaking fast. Wait, don't look at me like that. You thought I was going to use another word. No, you know who you are. Try to be happy. Try to be awake. Electrical. It's different. This is an electrical coupling. There are gap junctions, rapid, go in both directions. Some brain regions responsible for eye movements or the hippocampus and emotions and memory. This is we see these in developmental embryonic nervous tissue. Is basically establishing patterns and really constructing itself to be able to eventually advance upon the birth of the baby. Did you learn about the hippocampus? You did. So you anatomically you found out. What that is effect. That's memory. Where do we see damage to the hippocampus and what disease? That people get when they get older. Hint, hint. Alzheimer's. See, that's the area that's targeted. It's part of what system? It's a system that's associated with all your emotions. Did you learn about something called the limbic system? The amygdala is something there that's in there that's associated with the rage center, mammillary bodies, which are really part of your olfactory aspects. Smells evoke powerful memories. Smells make you happy. Smells make you sick because they go directly into your brain. Smelling salts wake you up. That's why, because it goes directly into the cerebral lobes. See, this is where you put the anatomy and the physiology together. Aha. Good. People got answers. So the neurotransmitter cause greater potentials that vary as to the amount and how long they stay there. And depending on that, they're either going to be excitatory or inhibitory. I'll make sure it says excitatory or inhibitory. Again, not everybody's going to play nice and just from hoping that you get the right answer and understand it. They're going to, acronyms are going to follow you around everywhere. Again, I particularly if you're going to a field where you have to do a lot of charting and documentation, you only can use, and in nursing they'll teach you about this, acceptable acronyms. You can't use your own shorthand. It's I don't know how it is in the computer age because I came from an age where it was all, we were handwritten notations or typed. But now, every time I've seen anybody in the hospital, you're charting electronically. There's a lot of paperless. I came from an age where there was paper forever. And here it is, just what I've been telling you. What does one neuron say to the other? Okay, fire, 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 don't fire, don't fire. Again, it seems silly, but it works. That's how it works. A whole lot of voices coming your way. Haven't you ever been in one of those things? Everybody's talking to you. Once you just want to turn around and say, would you please shut up? Again, using a descriptive adjective in between them. If you're like me. Trying to be humorous, but you're the sleepy class. So neurotransmitters binding opens chemically gated channels. Sodium in, potassium out. We told about that. Those are typically excitatory. Okay, they'll trigger an action potential if they reach threshold. Goes to that axon hillock or the trigger zone and trigger the opening of those voltage gated channels. And boom, this is what I spent ages talking about when we were together on Monday. Be happy you're not going to have me to kick around anymore for a while. We're getting very near the end, as the song says. Excitement. And foolishly, so far, somewhere like 47 of you want to have me for micro. Dr. Mauer's a lovely man. Please see him in the afternoon. He's smarter than I am. So here's what happens. So excitatory, those same sodium, potassium, those are the only ones we have at the motor end plate. Neurotransmitters binding to the receptor open chemically. These are the inhibitory or inhibitory postsynaptic potentials. Hyperpolarizing. Most of them are chloride. It can be just potassium, not as common, but chloride-gated channels let chloride ions move into the cell. Can't produce it. It hyperpolarizes it. It makes it more negative, less positive, whatever works for you. Those are typical, and that's why I alluded to before when we talk about sedative hypnotic agents, sleeping pills, muscle relaxers, Ativan, Valium, Librium, which was one of the original ones, Xanax. Names you're going to, if you're going into where you have to have prescriptions or understand them, you'll be sick and tired of hearing. You'll learn the generic name, and you'll learn the trade name, because that's the way people more commonly understand it, that are there. Typically, they work by that. Alcohol works. And you see, it takes it farther away from threshold. And they're showing you the chloride going in, and this one, the potassium going out. It does not occur simultaneously. It's one or the other. The chloride are definitely more commonly seen. Those are the ones to know about. That's the clue. Okay, and we summate them. We add them up. So we do everything else. Okay, cannot induce an action potential, but can summate, add together to influence, whether it's excitatory or inhibitory. Okay, and most time they receive them from both. Again, this whole idea of when you're taking that exam, unless you know what's coming at you, you look at the, this looks good, this looks right. Boom. You're gonna, and a lot of times it'll be, if you've already discovered an exam, most exams are like this. You can eliminate two, and if there's two or three left, that's where it is. And it's just, oftentimes that's good, because now you're making what's called an educated guess rather than a straight guess. But that's the whole idea of exam taking. You should teach a course of that. So, two types of summation: over time or over distance. That's temporal and spatial. Spatial is space. Temporal is time. Okay, one or more, this impulse is rapid fire. Before it can dissipate, another one and another one. Spatial, simultaneously over a long area. Okay, and so it doesn't matter whether it's rapidly fired or fired a bunch once over a large space. Both of them can conceivably produce an action potential. That's just the ways that it basically enables that to occur. And they're just showing it to you. I don't get a lot out of this. The rocking chair is interesting, but it's okay. I don't get a lot out of that either over time. It's basically, I think the only real question that I come about is the idea of frequency equals amplitude. Whether it's spatial or whether the summation aspect, I do not think is important. I will take a look at the exam when I do that recording to make sure you're aware of it. It's not, that's going to be over Thanksgiving break. We're going to get that stuff done. In between football games and an abundance of food. I can only hope. Probably one of my daughter's more raucous parties. So, this is very important as well. Repeated use of the synapse increases the ability of the presynaptic cell to excite the postsynaptic cell. Why is this important? When we get to neurotransmitters, you have to understand the way many of you are going to be familiar with have to do with something called the uptake. You get this break apart a little bit. The most famous of these are called SSRIs, stands for selective serotonin reuptake inhibitor. Effectively, this is the category when somebody is taking medicine for excessive compulsive disorders, eating disorders, ADHD, things like that, mild depressive disorders. These are extraordinary postpartum disorders that aren't as severe as some of the others. This category is a category where you see things like Paxil. The original one was Prozac. So these are probably ones that are, and they constantly change because we're constantly finding them. The pharmacy basically takes the same thing and tinkers with it so it doesn't have any side effects. Some get it for kids, some get it for adults. What happens is, what they're doing is they're inhibiting reuptake. What that means, it's going to lead to, if you're not letting the reuptake of the serotonin, it's going to stay in the synapse longer, and it's going to eventually, over time, have the capacity to alter receptor. Actually, to change the way that receptor works. That's the goal of a lot of this treatment. It doesn't always work. So a lot of times people are playing with medicines. A lot of people, I have so many people can't solve problems with a pill alone. Generally. Usually it involves, as a diabetic, you give insulin, oh yeah, one of these new remarkable weight loss drugs, but there's lifestyle changes that have to go. So repeated use of that synapse increases the ability of the presynaptic cells to excite. It makes it more easy to fire. So that's just one of the ways, and that's what actually it's modulating it or changing it as well. Fancy term use of modulation. So calcium concentrations increase in the presynaptic terminal, leads to more EPSPs or excitatory. Potentiation can cause calcium voltage gates to open on the postsynaptic, so it enables it. Calcium activates the enzymes, leads to more effective response, stimuli, long-term potentiation, learning, and memory, effectively altering that circuit over time. That's why, and it just drives me crazy. You have somebody who go, "Oh, I went to see my doctor, and they gave me this magical stuff. Let's say, for argument's sake, it's Prozac or Paxil, and how did you start taking it? Oh, last week. I never felt better. We call that a placebo effect. It doesn't work that fast. 2, 4 weeks, 6 weeks, 8 weeks. Average time between a month to 2 months to do this. But people feel better when they're taking the pill. That's what a placebo is. When you test medications in the last kind of studies, they basically will give you an inert pill and the pill that has the medicine. It's called a double-blind study. If you're not aware of it, you should be. Okay, double-blind means the patient doesn't know, the test patient doesn't know, and the doctor doesn't know when they're evaluating the patient. They enter the data into the computer, or in the old days, a third party with numbers and not names, and the computer then knows what's going on and assembles the data. That's what, both the double blind is the patient or the test patients don't know, and the examiner doesn't know. And you have a fixed set of questions. Did you feel this? Did you experience this? Did your skin itch? Did you have diarrhea? That kind of crap. Got it? So the idea, a lot of times, how many times happened to you? I got a terrible headache. Have you got a couple of Tylenol in your purse or in your bag? And you go, yeah, here. And 5 minutes later, you go, how you doing? Oh, my headache feels so much better. They took a pill. They feel better. That's a placebo effect. It doesn't work physiologically that fast. Not a lot does. It's such an important point, the idea of long-term potentiation. So I make a big deal out of it. Presynaptic release of excitatory nerve by one nerve is inhibited by another nerve. Yeah. Don't care. I'm going to release stuff. No, you're not. We're having a neuron fight. It's okay. It'll be over soon. So here they are. I don't get anything out of this. If this makes you happy, go through this. We've seen this so many times. Here's the other channels. Here's this. Here's that. Here's the action potential. Oh, thank God that's. I'm so pleased. A half an hour to get through the busy stuff on the synapse. This is where it all shakes. This is neurotransmitters. Okay, 50 or more, you only have to know 49. I'm giving you. See, that's the first one I got somebody to smile at me. You, oh, and where were you, by the way, on Monday? Yeah. What? Oh, really? Sure. Okay. I guess you're entitled. That's it. See, you may think I'm oblivious to who's here. By names, possibly. By where you sit and things like that, no. I've got the pattern. Why am I talking? You people are always here. The ones who are always here, I know too. Some of whom could take the day off. Ava's looking at me going, yeah, he's talking to me. So here you go. I am not. I may seem like I'm in another world, but I am not. Despite my wife informing me to take my head area and remove it from an orifice in another location. 50 or more neurotransmitters have been identified. Most nerves make 2 or more. So they don't always say fire. They might say don't fire, or, you can fire, but not next time. Usually related at different frequencies. So again, if there's an electrical aspect. And so we classify them both by their chemical structure, and we classify them by how they work. And usually that means, are they excitatory or inhibitory? So we'll simplify it. There are different categories. This is very interesting stuff. This is a very good sort of introduction to pharmacology. And for those going into nursing or any field where you have to understand pharmacy, that is a really hard course, by the way. Most of the students I'm thinking that's next term for the people who are a year ahead of you. They're doing pathophys this term, and then pharm next term. Those are bears. I'm saying I had this discussion with my wife, who's a nursing student, an LPN, and my ex, who was an RN with a BSN. For all of you, I appreciate this. You're new in the university system. Understand, can't be late for class. If it's a 9 o'clock class, on time is 10 minutes before. Oh, I have to leave early today. Unless you're doing something university approved or you have documentation, you're not going. It's all about that. You're very, very regimented. You can do 10 things right, and out of 11, and the 11th thing, they'll jump all over you. People, I'll say it again and again, you need to understand this. The people who are hardest on you are the people in your own field. They're always like that. I had zero tolerance for that. I couldn't stand it. Because I interpreted they thought I was smarter than I was. And I tell them off. It did not help me professionally. Okay? I made more enemies than friends. You want to make friends. So a lot of times if they're dressing you down, whatever word you want to use, reading you the riot act for a reason, just, yep, thank you for pointing that out. Please, don't give them a reason to think that you are a problem. I'm telling you from this, I have a lot of experience with this. I've been teaching nursing for 25 years. Trust me, know this. Okay, acetylcholine. We know about this one. The first identified, the best understood. They were taking frogs' vaguses and testing the stuff that came out and examining, figuring out what it was. It was vagus snuffle. It was acetylcholine. And you're going to see it's the major player, a major player in the brain, the only player at the neuromuscular junction, and the major player in the autonomic nervous system. So it's all over the place. It's a category in and of its own. Acetic acid and choline by an enzyme that you don't have to know the name is. But you do have to know this one, particularly for the tests coming up. Acetylcholinesterase breaks it down. Acetylcholinesterase inhibitors can be very bad news, particularly things like nerve gas, chemical warfare. Okay, that whole number. Please listen. Now we get into different. This is a little harder category to understand. We'll probably just take one. I know it's chemistry. Don't bother me. Do it. I feel compelled. That's an amino acid. Amine group over here, and an acid group over here. Most of the time, when your body takes one of those in, it locks off the amino group, and then it puts it back on when it needs to. Basically, we absorb amino acids. We'll get to that in digestion next time. The difference here is what the biogenic amine is. They lock off the acid. So basically, when you ingest proteins, to make sure you have the ability to make these, proteins are absorbed by as their component parts, which are amino acids. That whole thing about essential amino acids, the 8 or 9 of them that are essential, this is why it's important. Because you have to have those to make certain things. These are called catecholamines. They got that name. I'm not sure why. But originally, when we used to think that the cause of people with depression is they were not getting enough of these. Okay, particularly dopamine and norepinephrine. Those are the ones that are made. Remember that substantia nigra in the midbrain thing? That's why this is important. And they felt that that was a lack. And they had a thing years ago that you don't have to know about called MAO inhibitors, monoamine oxidase inhibitors. They're kind of like the acetylcholinesterase for these guys. Okay, and they tried to make more of those available. Not nearly as effective as those ones I was pointing out up there, those SSRIs. Short course. So dopamine, norepinephrine used to be called noradrenaline. Epinephrine used to be called adrenaline. And I'm telling you that because it's important to understand, because you're going to see that name's going to show itself when we get to the autonomic nervous system. We didn't forget the name. This is the amino acid. It's called tyrosine. Tyrosine is super important. Thyroid hormone is made from tyrosine. So tyrosine is really essential. And this is one of the things we used to know. Certain foods are rich in tyrosine. Because of those, the foods that were rich in tyrosine would sometimes produce excitatory stuff. They would sometimes certain people who ingested a lot of this, they might maybe make their blood pressure go up, their heart rate accelerate, things like this. Understand that this is where food science comes in, and certain people are troubled by this. The flip side of that are these are called indolamines. So the catecholamines are made from tyrosine. The indolamines, serotonin, which I showed you up there, and this guy, histamine. And everybody's heard about histamine. Because everybody's heard about antihistamines. Ad nauseam. Okay, they are both. Serotonin is made from tryptophan. Perfect time to talk about tryptophan. There's a very funny show called Seinfeld that maybe some of you occasionally watch reruns of. They did a whole episode about this. I don't know about you. You see, a lot of, when we used to eat a lot of turkey, which contains tons of tryptophan. What does that do to a lot of people? I'm sure the red wine has something to do with that as well, but we digress. After they have a big Thanksgiving dinner, they are what? They are sleepy. Correct. Seinfeld, and they wanted to play. This lady had a friend of theirs had a toy collection they wanted to play with. She didn't want them to. They kept bringing her turkey and red wine, which has tryptophan in it too, so she'd sleep. You could play with the toys. It was a very, very clever episode. And so the serotonin does play a role in sleep. There's a lot of different serotonin receptors. That's a little bit more of an advanced concept, but I will talk about it. There's a whole lot of, and a lot of these medicines that you hear about that are used they're advertising ad nauseum on TV, okay, for different kinds of problems. Okay, really they target different serotonin receptors. Okay, so there are subcategories of receptors. This is way advanced This is the kind of stuff you'll hear about in pharmacology. That's there. So serotonin comes from tryptophan, histamine everywhere. Histamine is a neurotransmitter in your brain. Histamine is the chemical that is released, as you will learn in AP2, from cells that are called mast cells. They are cells that are in the bloodstream that are laden with histamine granules. And when you have an allergic reaction, they explode and they cause blood vessels to dilate. Okay. And in doing so, depending if they're clustered in your lung, your bronchial area, you get asthma or you get anaphylactic shock, which is a very severe, immediately life-threatening acute asthmatic attack. Not that any of them are good to have. Okay? Or they can cause hives under your skin if there's abundance in your skin. Or if they're upper respiratory, we get the usual stuff. Why we take antihistamines? Now we at least have antihistamines, like I take a Zyrtec every morning, that don't make you drowsy. The old ones, the Benadryls and stuff like that, which is called diphenhydramine, made you drowsy. Okay, we even take them for your stomach. There's one called Pepsid and Zantac are ones that block receptors in your stomach because histamine actually makes your digestive tract more active. You get all of this, or you should, in AP2 physiology. If you're confused about it, I am here as a resource. I am more than happy to do that. Just have to identify. Hopefully, no, don't say it. I don't want to make fun. All widely used in the brain, play roles in emotional behaviors, biological clock, used by some, especially norepinephrine, we will get to. So they got a fancy name that comes from adrenaline. They're called adrenergic. And the ones that respond to acetylcholine, we're going to learn, are called cholinergic. Those are unfortunately terms you have to know. It'll make your life a lot easier in pharmacology. Trust me. I'm good like that. And antibiotics, you're going to love micro because I go crazy with antibiotics. And antivirals and antifungals and stuff like that, which I know a lot about. And imbalances are correctly are associated with mental illness. They used to think, again, that depression was best treated by making more of these. Now we are very much, I'm going to say, satisfied, probably the right word, at least it's promising. They've been around for a while. They used to even think they were safe for pregnancy. My daughter has, at that time, I mean, it's not that it magically disappeared, but it was very prominent when she was a teenager, a variant of bipolar called bipolar 2. Bipolar 2, so they were treating, and one of the things, unfortunately, we were told about in bipolar, but stupidly, doctor and nurse for parents didn't understand, was that they are very sexually active. Hence, granddaughter, by the time when daughter had her daughter, as I told you, before she was 16. Which makes her a very attractive, not even 40-year-old grandma. But we digress. So she was taking this, and they said that she could take it, like maybe it was Prozac or something like that, through pregnancy. Not now. Now I think they've gotten to where there's a whole lot of, even they're talking even now about limiting Tylenol. She was allowed to take 2 Tylenol a day. Nothing for morning sickness, the usual, whole ton of water and a bunch of crackers. That's about the size of it. And so she delivered, my granddaughter was born, oh shoot, she'll be 24 on December 3rd. Sorry. On that, I have to, this is when I need something in the coffee. So that's the whole idea of imbalances. Histamine, not so much. Amino acids themselves. The amino acids themselves make up all the proteins. Therefore, it is difficult to prove which are neurotransmitters. Consistently, there's one called glutamic acid, another called aspartic acid. When they're dissolved in water, we use the terms glutamate and aspartate. It's not magic. Okay? Acetic acid, vinegar in water is called acetate. The AT just means it's dissolved in water. That's all. So glutamate and aspartate are the names we give to them. They are consistently excitatory. Glycine is one. And GABA. We always say GABA because it's a pain in the neck to say gamma amino butyric acid. Okay? They are consistently inhibitory. So these are the ones we look, glutamate particularly. When nerves are damaged, they tend to push out more glutamate. This is what happens in patients after strokes. And the glutamate is basically telling the nerve that's going to your muscles to keep firing. Glycine is the one that tells it to not fire as much. It's the reason people develop post-stroke spasticity. I'll talk a little bit about that when we get to the next chapter. Today I sent you the chapter 12. I'm going to have to not cover as much of it as I might like to, because there's just too much to cover from where we are in this particular term. And I think that I was looking at the final exam today. I'll probably modify that because you had a lot of that stuff already in lab, and it's somewhat redundant. So I'll give you what I think is important and try to focus more for our test on this chapter and the other chapter. We'll stop here with the amino acids, and I'll probably start back with them next time. All right, thanks. Have a good one. See you Friday.